Hello and welcome. My name's Neil and my handle is Wiley11. And let me start by saying that everything I do and say on these videos, I accept no liability whatsoever. So if you're following along trying to do something or take some of the advice I've offered, you do so entirely at your own risk. This is my attempt to give back to YouTube for the help and assistance that YouTube has given me, and I'm trying to be careful. If I slip up, then you know I'm human, and you'll have to forgive me for that. So yeah, that's what this is. This is well-intentioned and well-meaning advice, and you follow along entirely at your own risk. And if you're not wanting to do that, then by all means click this off and off you go. Thanks for tuning in. Hello and welcome. My name is Neil. My handle is Wiley11, and we are talking today about Project Zoomie Subproject Dash. Right, so let me just put my disclaimer in here. Everything I do and say on these videos is well-intentioned and well-meaning advice. In terms of engineering process, I am a qualified engineer in terms of I have a degree in it, but I do not have an industry qualification in engineering yet. I'm a graduate engineer. So this is for my own edification as well as for yours. So you can learn at the same time I'm learning. Because I am relating an engineering process in this series, everything I say and do, I accept no liability for whatsoever. If you do something, you do it entirely at your own risk. And if you can't accept that it's at your own risk and liability, then click this off and off you go. I accept no liabilities at all, whatever. Right? So bear with me and follow along. You'll find this quite an entertaining journey about how I got from A to B to C to D, following a good engineering process and software engineering and the whole thing. The whole thing is in the video. I'm taking you through the lot and how I've done it, which is a good engineering process. But once more, I accept no liability for anything. If I've inadvertently infringed on someone's copyright or whatever, it's completely innocent. It's not my intention to rip anyone off or do anything. It's my intention to give well-meaning advice back to YouTube. And that's all this is about, is repaying YouTube for the help and assistance which YouTube has given me. So once again, if you can't accept that, click this off and on your way. But otherwise, stay tuned and buckle up. Project Zoomie is a 50cc Piaggio Typhoon bike, and that was the outline of my project, my control document. And today we're looking at this task here, the subtask, which is repair the dashboard wiring and fix the clock. So rewire the dashboard, in fact, and fix the clock. The reason we need to do that is because this is a spare part that I've got from a wrecker, and you can see it's made of plastic and it's got copper on plastic, and this piece of plastic has been, this is a spare one, it's the same age as mine. Mine looks a lot worse than that. It's completely shot, and I've actually had to bridge solder across the brakes because it's brittle and there's bits and pieces missing from the circuit, and I've just had to bridge with wire, all sorts of things, you know, it just looks terrible. And of course you get these little bulbs. You get these little bulbs in it. Now, I don't know if you can see the difference. See if you can spot the difference between a good bulb and a bad bulb. Blown, not blown. Right? And the problem is they blow these. And the reason for that is they short out, because that's actually exposed to the elements behind the dash. And, you know, any water gets down into it and poof, you blow a bulb. So I'm going to rewire it, I've decided. So I'm going to just give you a quick intro here to this part of the project, which is rewire the dash. I set a deadline for the 20th of July. That's been and gone. We had some reasons for that. And now I'm just going to take you through my introduction video. So sit back, buckle in, hang on, and let's get through into Project Zoomie's dashboard.
Right, so I'm just looking to catch you guys up here on Project Zoomie. What I've got here is a dashboard out of another Piaggio, and you can see it's pretty grubby and it's covered in crap and shit. But you'll see that on the back of him is this thing, which is what I actually wanted it for. I wanted this circuit. Now the problem with this is, you might be able to see this. See that? The tracks break. It's old, it's plastic, and they're brittle. And the tracks break. And on Zoomies, I can't tell you how many times I've had to get that off and solder him up. So what I've done is I've got that off, and I've traced out what the circuit is. There it is there. That's really messy, I know. But that's basically what that looks like. So when you line this up like that, right, that's where all the wires are going. Now you can see, sorry, I've got that upside down like that. Righto, so you can see that's that bit that goes around there, and it comes back this way, it goes up there, and it's got 4 pins there and 5 pins there. And that's that whole circuit kind of mapped out, and I know what I'm doing with it. So that's good. Now there's one more little doogie here that I wanted to talk to you about, and you might be able to see it on this dashboard. It's got a thing there that says time. And on Zoomie, I got a bit of black masking tape over that, because I lost the clock. I pulled it out of him, and unfortunately disintegrated in my hand when I pulled it out. It was so brittle and old, it was just no good. So this one's still got the clock intact. Here it is, and it's still got all the bits, except that it's missing this cover. So without that cover, it's useless to me because I can't put a button cell in there. So what I've done is I've got a bit of acrylic here, and I've just cut it using the soldering iron. In fact, I've just cut that out, and you can see I've got 2 holes in there. And what my plan is I'm going to solder 2 wires, one on the negative and one on the positive, and bring it out of the clock and attach it to this beautiful button cell, which I'm going to mount inside something that sits outside the dash. So that, as you can see here, to change the battery in the clock, you've got to pull your whole dash apart. You've got to pull all that up. Now the needle off the fuel gauge has gone missing off this. But you can see you've literally got to pull your whole dash apart to change a battery in your clock. Because it's just a button cell battery. That's all it is. So, you know, what I'm going to do is solder those wires on. I've got a bit of flux there. I've got a couple of wires. Here's a red one and a black one. I've got a button cell holder. And the idea is to bring this outside of that carcass and put it somewhere up under the dash where you can just undo something and get to it and then just change the battery and then put it all back together without having to undo a gazillion wires, you know, and bolts and screws. Because to get into this, you got to pull the whole handlebar assembly apart just to get into that. And you can see here the cover fits over the top of that. You know, it all goes together nicely, and you know, for what it is, for when it was built. But whoever the hell thought that that was a good idea, yeah, Italian, whoever you were, I'm sorry, it wasn't. You know, it just wasn't. You needed to do something. It's good that, you know, you needed to do something in the way of running up harnesses. You know, that this was all just a harness rather than this plastic piece of crap. Now what I'm going to do is I've got these, right? I've got these. And what I'm going to do is cut these to size around all these gaps to hold the components that I need to hold. Right, so this will hold the components. So I've got all these bulbs. See these bulbs, you can see here, here's one that's blown. You can see that one. He's blown. And let's put him up against one. As you can see there, one's blown, one's not. See if you can guess which one's which. Right, there's the blown one there. He's blown to the shit house. And every time one of those blows, you can pull your whole dash apart again. So my plan is that I'm going to replace all that with LEDs. I'm going to do up a circuit board. I'm going to put it all in place. And the other thing is there's 1, 2, 3 lights in the dash. And at night when you're going along, you can put 4, 5 lights in the dash, 6 lights in it, just as easy. You know, bugger all trouble to do it. You can have a well lit up dash so when you're going along at night you can see what the hell you're doing, which is not a bad suggestion. And apart from which the LEDs will be a bit brighter anyway. So here's the plan. I'm going to do the clock today. That's as much as I want to finish today. And then tomorrow we might think about starting this circuit. We've got a circuit diagram that I've done on fritzing. And I'll do that on the computer with you. But I just want to keep this short today. I just want to do that. I want to get that all put away before Mrs. Wiley comes back. She's out doing a bit of shopping at the moment, so I need to put all that away, back in the plastic bag. I need to clean all this up. Sheet. Right, let's go. Technical data. That'll do me. Beautiful. That's what I bought. That's exactly what I bought. Up to 4 kilovolts. You're freaking kidding me. Up to 4 kilovolts. ESD. Oh, God. Well, I can definitely. 4 kilovolts. Unbelievable. Oh, I don't believe that. Let's have a look. Let's have a look. Hang on. Peak forward current. Okay, they're rated to 100 milliamp. Okay, continuous is 30 milliamp. So my thinking is wrong straight away. See that? Because I know I've had 200 milliamp through these things and they were fine. Now continuous current is 30 milliamps up to a maximum of 100. So if I put a 50 ohm resistor in there, I'm nowhere near big enough. Okay? Because I've got 250 milliamps at 50 ohm. So my maximum peak forward, and I want to get that down to 30 milliamps. So if I've got 12 volts, right, I'm going to do the math out properly. If I've got 12 volts, and I've got to get down to 0.030, I can't do that in my head. I can't do it in my head. I should be able to do it in my head, but I can't. Oh, no, terrible. Righto, so I'm going to the calculator. I've got one of those over here. Right, so I was completely wrong. Completely full of shit. Have a look at this. Forward voltage combination volts at 20 milliamps, right? It requires a minimum, right? A minimum of 2.8 and a maximum of 3 volts. So there's no way they'll even handle 12 volts. How freaking amazing is that? Now the beauty of it is, if I put resistors in parallel, I get a voltage divider network and I can share load, right? So I need to equally divide it by 4 in order to get it down to 3 volts. But it turns out that they're only rated to 30 milliamps. Sorry, 300 milliamps. Here we go. 30 milliamps. 0.30, and when you divide 12 by 0.03 you get 400 ohms. So I was way out. I was never going to get, this thing was going to explode in my face. Now you see the value of checking a data sheet.
All right, so now I know I need at least 400 ohms. I'm actually going to go up. I'm going to go up to a 512 ohm resistor. I think that's the, it's good. You can go higher. You can't go below 400. Now, to get to my 3 volts, I need to divide it by 4 because I've got 12 volts and I've got a maximum of 3 volts. So if I have 4 of these things, I can get down to 3 volts. Okay, voltage divider, voltage in equals voltage out. If I divide it by 4 and I keep them equal, then I'm going to get maximum of 3 volts in there. So that's going to work. Now the thing of it is, I have to match the resistors. They have to be exactly the same ohms rating. So I'll need to put them on my ohms tester. And they need to be the exact same value. Otherwise I'm going to get a difference. Right, I need it to go exactly to 3 volts because going back to this, maximum forward voltage 3 volts. Current, forward current versus forward voltage, right? So here's our voltage, right? So if I go up here into 3.5 and up towards this, I'm getting 25 milliamps. Right, so they're saying that if I'm feeding it more than this stuff, that this thing's going to blow. Right? I don't know. Here we've got another one. What have we got here? Relative intensity. These are lumens. These are lumens. And this is our forward current. Now that doesn't make any sense. So as we get up to 50 milliamps, it actually gets dimmer. I don't know. That doesn't make any sense to me. Righto, so this is what they're saying is going on. Righto, fair enough. Okay, I'm not worried about any of that stuff. Righto, so it seems to me like I've got to get the voltage down to around 3 volts because that's our maximum voltage. And in an indicator, that's not continuous. Now, that's in the dash, that's interesting because I'm going to have six bulbs. You're going to have 2 volts each. You're going to have 2 volts each. So in the dash, that's a big consideration. I've got 12 volts. And it said there needs a minimum of 2.8. Right? Needs a minimum of 2.8 volts. Where did I see that? And I've got 6 bulbs, so I've only got 2 volts each. Here you go, minimum 2.8. Oh, okay. That's at a supply of 0. Over here, right, so we've got a 3 amp circuit. So I can get 3.4 to 3.6. So I'm cool. Right, so I'm back again on these LEDs research. Now, what I ended up doing, I dug around in the drawer, and you can see here quite clearly that it says 3.4 volt max, 3.2 volt, 3.4 volt max. So I was completely out. I thought these were 30 volt ones. They're not. Okay. Now I know I can get 30 volt ones, but I'm making do with what I got. And I know that those LEDs are plenty bright enough. So what do? Well, the answer is I can create a voltage divider network. I can create a voltage divider network which will limit the voltage from 12 volts down to 3 volts. And the way you do that is, as I said, you divide 12 by 4 and you get 3. So I have one resistor, that's a third, a quarter. No. I have one resistor that's 3 times the value of the other resistor, right? That gives me a 4, right? And that resistor there goes in circuit, and then off the back of it, I've got the other 3 in circuit. right? So I've got my voltage divider, which will give me 9 volts that way, 3 volts that way, right? So the big resistor goes there. So then I've got me 3 volts, and then I've got me 3 LEDs, and then I can use my 40 ohm or 50 ohm resistors across my LEDs. So I've got my current limiters going. There you go. So it becomes a more complicated circuit. So I have my circuit, I drew it up, it's got to change. Where did I put it? I don't even know where I put my circuit, I threw it away, did I? Okay, so this is what I thought originally, which we now know is wrong. And what is wrong is this. So what we have to do, wrong, we're going to take that out, right? We're going to take that part of the circuit out, and we're going to come this way off the thing. Bear with me. Right, so it was some considerable time after I shot that, and if you were bearing with me through the original, I do apologise, because this is where we ended up after all the fiddling. And what I've ended up doing is this circuit here, right? This circuit here feeds our data, feeds our 12 volts. So here I've got a switch, and even this has changed, right? So we've modified it from this too, but for the moment this is what I've drawn up. I want some kind of a switch to go between indicators and and dashboards, because I want this test circuit to do both jobs. I want to isolate my blinker control unit up here. I'm doing this with an Arduino, so it's protected by a diode here. So this is the 12 volt rail here, this is a 5 volt rail here, powering my blinker circuit. So when my blinker circuit's on, you can see it comes down through here. It won't go back up that wire because that switch will be up there and that'll be open. So it'll come down this way and it'll hit this voltage divider network here. So over here I've got a 500 ohm resistor, and over here I've got a 1 kilo ohm resistor. Plus I've got all these resistors in my circuit. Now what I've since done is I've gotten rid of this resistor. It's gone. And I've added this potentiometer here to vary, and that becomes my dimmer switch. Right? So I can vary the amount of current coming down this network. But I've also got the ability to change from my 2 globes for my indicator to my 6 globes for my dash. So this switch and this switch work in tandem. Alright? So when that switch switches it up to dash lights, which is this one here, this switch will also engage. So I'm going to change this design. I'm going to have 3 of these. And I want them as outputs so I can see them switching in and out, because I might change it again somewhere down the road. But this is just my test circuit. So where we got to with that was we decided that was correct, and then we changed that. And what's going to follow is the change. What about these LEDs? You know, I can live with what's in the cupboard. I can do that. So I can use these cells. I can do, my thinking's good. That's encouraging. You know, you got to test the specs. You know, you got to test it. You got to make sure that you're going to do what you say you're going to do, and things are going to work. Now that's a 3 amp battery, 3 amp hour. So it just means that you know, it takes 3 amps to charge it, fully charge it. It can provide 3 amps draw for 1 hour. It also means it can provide 1.5 amps draw for 2 hours and 1 amp draw for 3 hours. You know, that's what it means, 3 amp hours. So per hour, it can be drawn down till it's flat. It can provide 3 amps of current, continuous current for 1 hour. So, or 1 amp for 3 hours, if you like. That's what it means. I don't know what Zoomie's draw is. I don't know what the circuit draw is. I don't know what the amps are. Maybe that's something I'll have to test. He's an old bike, you know. Again, I think I'll get a clue from the wiring, right? Like if it's 1.5 amp wire, 1.5 amp rated, you can bet your life it's drawing less than an amp, because it'll be rated like whatever the thermal rating is on old school, and this is old school. You know, Italians, whatever else you say about Italians and the interiors of their cars falling apart, which they do. I haven't had a single Italian car where the interior just hasn't disintegrated, but I love Italian cars. You know, I love them. But their interior work is terrible. It really is. They just disintegrate. Anyway, the wiring and the engineering in Italian stuff is good. It always has been. It always will be. And they do a very, well, in most instances where they're not using a bit of plastic with some copper on it, which is what they did in the dash, it just falls apart. It's no good. You got to use proper. But the wiring itself, it will never catch fire. It'll go for a long time, and it never has caught fire. So I can trust that this wiring, it's proven itself. It's been going for 16 years, and it's never had a problem. It's always delivered power to that particular, and hasn't failed, hasn't broken, hasn't overheated, hasn't melted. None of that stuff's been going on. So we're going to get the rating off the wire on the bike, and that'll give us the amps that we need to worry about. And then we can double check the circuit for the specific amps that we're getting off the wiring. And I'm pretty sure it's 1.5 amp automotive, rated to 1.5 amps. And the temperature ratings and all the rest of that go along with it. But it's if you look at the indicator wire, I think it's about a 2 mil. It's about a 2 mil wire, and I'll go down and check it with the vernier. I've got my little vernier calipers there, and little digital verniers there. I'll go down and check the thickness with those, and then we'll get into the next part, which is going through and developing up the circuit, the test circuit with the correct wiring, etc., etc. But for now, it's all got to go on a breadboard. I just want to test that my thinking is good. The numbers I've worked out here are right. I'm worried about this 1500 1.5k resistor. Worried that I've not got the voltages correct. You know, but we'll find out. That's why you've got a test circuit. And I'm going to sit around and enjoy a cup of tea. Now, I'm not going to take you through programming the Arduino. That anybody can do. You just plug the damn thing in. It'll come up on the screen. You've got the Arduino IDE, the desktop IDE. That's the software. You download it from the arduino.org. Make sure you get the current one that's rated. You know, they've got different versions. You've got an Apple version. So there's an Apple Mac OS X version. There's also GNU that you've got to sort out, and there's a Linux one, and then there's a Windows one. And the Windows one is just basically, you know, unzip it and put it in a directory, and it just works. They don't use the Windows libraries that come with their own libraries, which is kind of neat. I don't know. I don't know. Linux guys talking to Windows is you know, they don't like that. But I don't know why the feud happens. It just does. And I think I was trying to download free software, and I know that Camtasia works well in Linux, and it does. It's a great bit of kit. And I tried to download it from some site and put the Windows version on. And the first thing that happened was my antivirus jumped all over and said, "This is full of viruses." And I was like, "Oh." That was the first time I've ever heard of Camtasia being full of viruses, but I suspect it was the site that I chose to download it from rather than the actual Camtasia software. But I'm cold. My feet are cold. Because my feet are cold, I'm cold. I'm going to pause this. I'm going to put some bloody shoes on so I can get my feet warm. Just give me a sec here, folks. Just going to hit pause. I just want to show you the shoes I'm going to put on. These are my work boots. As you can see, they're in good nick. I clean my boots. I look after my gear. You've got to look after your gear, because if you don't, you won't have it very long. Don't loan it out to blokes either. You know, if you can avoid loaning your tools out, don't ever loan your tools out. Or if you've got a bloke that's always borrowing tools, make sure you're giving him the one that you picked up in the bargain bin, that you don't really care. Because I think I showed you a set of chisels I loaned out to one bloke. He kept them for nearly, well, I don't know, 4 or 5 years or something. He gave them back to me. They were completely rat shit. They were broken. They were blunt as a set of chisels. But I only paid like $5 for them. Picked them up in one of the. I always look for the cheap bins when I go to the hardware or go to the parts place. I always have a sticky beak in the cheap bin, and if there's a cheap spanner or a cheap something, I'll pick it up for $2 or $4 or whatever. You know, I'll buy it. I've got a whole bunch of cheap tools that if someone wants to borrow something, I'll just give them one of the cheap ones. I never give them a good spanners to people. Right, so I'm back again. What I decided to do before I ran downstairs and used my vernier calipers to find things, I thought I'd get online, and you can see here I've looked for specifications on my blinker wires, right? Because those wires are the same for the brakes, and I've seen them before, and you can see here in any of these images that all of these wires are the exact same specification. Now to me they look like 3 or 4 mil, you know. But I got into this workshop manual here, Piaggio Technical Notes and Workshop. This is published by Piaggio. And this was put out on their Vespa series, but it also applies to the Piaggio Typhoons. 2-stroke manual engines, which is us. This is us, 2-stroke manual engines. And we're talking in the electrical systems here. And if we come down, now I've lost the spot where I was reading it. Here, these tests here are of interest. See here? So they're saying that the output is between 1.5 and 2 amps. And they can reach voltages of between 25 and 30 volts. Now, I find that very interesting. 1.5 and 2 amps is what I've been guessing. And now I've got some confirmation that it's correct from a technical reference manual, which is at this address here, right? So you guys, if you're looking to verify this, we can see it here, that the bike's current draw is between 1.5 and 2 amps. And we can see here that there's AC circuits which are regulated, right? So both the DC is half-wave rectified and regulated. Okay, so we've got both of these systems in play. But the point is, it's 12 volts. Regulated and rectified. So when it becomes AC, it becomes somewhere between 25 and 30 volts. 26 and 30 volts. So to me, it looks like standard automotive wire that we can just go out and buy straight off the shelf at any auto place. And that's good, because that means I can just buy the regular. There's nothing special, fire ratings or anything like that I've got to worry about. And I've just got to match the width using my verniers. So I'll work out whether it's 3 mil or 4 mil or 2 mil, whatever it is. I'll get my vernier calipers out down there. And I know that I'm not going to worry. It's just got to be automotive wire. I've just got to make sure that I get the correct. I can't use speaker wire. All right, can't use speaker wire for this. Got to use proper automotive wire. And so that'll mean I'll have to go down and I'll have to buy the actual wires. But even better, I don't know where it is now. I think I put it in Project Zoomie. Just give me a second. In D drive, back up, camera, pics, camera roll, Project Zoomie. I found this. And it is the correct wiring. I've already double checked it against what I understand it to be. It's a complete wiring diagram for the bike. There it is. So I've got the whole wiring diagram. I can see exactly that my thinking's correct on this wiring. The fuel gauge was a little bit funny because this here, if I trace these wires here, the two wires that I thought were common ground were actually coming from the fuel sender unit. So down here, this is coming from the fuel signal. Well, that's a turn signal relay. My God. Why would that go to the fuel switch? That's going to where? What's that? Horn switch. Well, I give up. Are they ground wires? What's this? This black wire I thought was the ground. Right, so back again, sorry. What I'm trying to do is just make sense of this thing. And we're talking about this fuel gauge here and trying to make sense of these wires. Now what I've realised is that this wire here is joined with this wire. See, it doesn't cross it. It's actually joined onto it. It's a really confusing wiring diagram from this perspective. And what all this is all ignition wiring. So you'll see here it goes up to the ignition switch. So what this means is that you'll only see the fuel gauge when the ignition is on. Likewise, you can only use the horn when your ignition is on, the turn signals when your ignition is on. Right, so none of these relays will activate, none of these switches, none of this stuff will activate. Oil level indicator, all this stuff will only activate if you've got ignition. That's what that means. So I was a little bit confused there for a sec. End of confusion, not confused anymore. So these black wires are definitely ground wires. What this means is that this second wire that I thought was a ground wire was actually an ignition wire, right? So I've got to be careful that I don't confuse that in my wiring diagram. It's not a ground wire, it's an ignition wire. And I need to modify my wiring diagram because I think on the thing, on the dash, this is the only instrument that makes use of that ignition wire, right? It's the only one, is that fuel gauge. The rest of these all come off their various sender units. So that sensor will only activate off of its gauge, but the gauge will only activate off of ignition, right? So there's the oil level thing. It'll only activate off ignition. Here's the, oh God knows, ignition control unit, right? And obviously that only activates off the key, off the switch, right? So all of these things, it's got an auto choke. I didn't know it had an auto choke, but it's got an auto choke. There you go. Well, that's got its own switching stuff though, but that's coming off this major. Okay, it's coming off the main regulator, and that only activates off the ignition. Well, what do you know? All right, so I've said enough. I've worked it out. So that's just to make sure that this fuel gauge only turns on when you turn the key. That's all that is. Righto, end of confusion. Let's just stop this recording. Okay, so what's going on here is I've been down and I've measured the wires with my digital calipers, and I've taken a quick pic here for you to look at, and they're 1.5 millimeters each, but you can see here that the indicator wires are actually doubled up. So there's two wires running to the ground and to the indicator. So I'm going to check that wiring diagram just one more time and see why I've got two wires going to that turn signal's actual bulb. What's going on here is we're now up to version 3 because we found a solution for the 5 volts that doesn't involve this. It turns out if I do this, I need to do current regulation behind that, and I don't have that option. So this is now going to change again. Just going to duplicate this. All right, let's come over here, but we'll put it out here. And ground is still going to be fine, but instead of this going, this is going to be 500 milliamps. Let's see. Up here we want to inspector. Righto, so instead of that being 12 volts, that's only going to be 5 volts. And it's going to be 500 milliamp. Right, we got rid of that 7805. We're going to have a second voltage source. So now we've just got to wire him in. And he's going to have an orange wire. Orange, please. Thank you. Right, so that's going to be our 5 volt source is going to be that one. And that'll continue on down. Come on, just go where I want you to go. It'll come down here to the switch. So I need to join that onto that. Alright, so let's get that to work where I want it. I want that there, I want that there, I want this to bend at that point, and life's good. So we're once again wired in, and here we need this to wire into this point here. So we can just drag that across, we can drag that across up here somewhere. And we can drag this down a little bit and just drag that into the end of that. What did I do wrong there? Actually, I didn't do anything wrong except that that wire color is the wrong color. That just needs to be black. Right, so we're grounded, everything's good, life's good. And we can just move on. That's version 3, which is now our final version. Right, and today's date is what? What's today's date? 21st. 21st. I'm not keeping the previous version because I've already got it. Okay, so file save. That is our new test circuit. This is our Belkin power supply that we found during our cleanup today. We had a big cleanup and we solved the problem of the 5 volt supply. So we've now got a USB power supply, which is brilliant. And I've actually got USB monitoring equipment coming in, so that'll be good too. Bit croaky, it's getting a bit late at night. I'm being a bit quiet, but I just want to get this down and done and dusted. Right, so we're done. Right, so I'm up and recording again. I want to talk you through this design. Real quick, I always put in a header on my schematics. This is a schematic that we're looking at. So this is test the LEDs, the date and my initials and version 1.0. This is actually version 6, but this is the first recorded version. Actually, I'm going to change that right now. It's going to be version 2. Because version 1, I've already got a drawing of version 1. I've shown you that. And now I've changed it, and now we're at version 2. Now, what concerns me about this is that, as I was saying, in the research I found that we can get up to 10 amps. And there's no way I want 10 amps hitting this circuit. None. You know, like if 10 amps comes down this red wire here and hits this circuit, okay, what'll happen, these switches won't be in the road. This is going to come straight through to this point here. And what I've done is I've changed this to an inline potentiometer of 5k. So I can vary the resistance to drop that. The more resistance I put in here, the fewer the amps that are getting through to the circuit. So if I put a variable resistor here, I can set it from 0 to 5k. So I've already got this resistance here to pick it up at close to 500 ohms. The closest I can get is 470. I don't mind that. So I've got a minimum 470 here. All these are 220 ohms, so I've got 440 versus 470 as a minimum. So I'm pretty much halving it. That's with that set to 0. But if I wind this up, I can see how dim or how bright these will flick on and off as an indicator. Now, this is at pin 13. If pin 13 is on, well, this must be low. So if pin 13 is active, so I'll have an active status, which this will be the opposite of. In the software, I'll control it by saying pin 13 status, active, so it'll be a boolean, which will be true or false, active, true or false. If it's not active, then it's fine for this one to be on. If it is active, this one must be off. So that'll be controlled in the software in my Arduino. Here I've got my voltage regulator, so I've got two lots of 5 volts. I've got 5 volts supplying the Arduino and 5 volts supplying my digital switch. So I've got this digital switch. It's only ever going to have 5 volts, so no need to put a rectifier diode here, right? No need to put a voltage protection diode in it, because 5 volts isn't going to worry the Arduino, but 12 volts might blow it up. Right, so yeah, so that's my circuit board. It's going to be my test bench, and we're going to just go hard and build this thing up. I've got all the components here necessary to build that now, and I'm not sure what my power supply goes up. I don't think it gets to 10 volts. But what I need to do with this test board is I need to drive these circuits to failure. I've got enough components. I want to know at what point will they fail. So my unit test will actually be to drive it into failure to the point, and then I'll measure the resistance on this potentiometer. So I'll start it at 5k at 500 milliamps, and then I'll, in terms of current. So I can set my current limit to 500 milliamps, and from 5k at 500 milliamps, I'll drive more and more until the full 500 milliamps is being shared in this voltage. So when that's 0, that'll be split there. So it should be about 200 odd milliamps getting through to these things, which they should handle that no problem at all. In fact, I know that I've driven these all of these LEDs, I've driven to well beyond 200 milliamps in the past. But I need to test it and make sure that if it gets hit with 10 amps, what's going to happen? Well, I can tell you, I've got a crystal ball. They're going to go poof. This circuit isn't designed to take 10 amps. I can tell you that without even trying. Okay, so what I want to make sure of is that if I get 10 amps down there, that I'm siphoning.
Right, so 3 volts was a fail, and I'm about to show you the little test I made using a 3 volt power pack, using that latest schematic. And my solution was actually this thing here, which, as you can see, is one of these Belkin generic charging units for a bit of Belkin kit that I had. I think it was a Bluetooth thing. But you can see here it accepts a USB plug, so it's providing 5 volts. So there's a 5 volt power supply, which is voltage regulated, isolated, switch mode. It's safe, it's protected. I don't have to worry about current, I don't have to worry about anything else. So it'll switch up and supply whatever's being drawn, and it won't draw a hell of a lot in terms of just powering up that Arduino. It's not going to kill it. So that's the solution to the power supply thing. So I'm going to take you through the little 3-volt test and show you why I've solved it with this. And I actually finished cleaning up this afternoon, so I can actually find stuff, which is good. I'm in a good place with finding stuff, which is, you know, excellent news. But this lives over here, and it stays there until I need it. And I've really cleaned up. I've got everything where it belongs, and I've got some wiring over here that's still got to get dealt with, but I haven't found a permanent home for these wires, and the problem with that is I've got so many of them, and I've got to come up with a better system. But at the moment they're all just sitting in a bucket over here, and when I get into that I'll probably end up putting... Okay, so I wanted to talk you guys through how Project Zoomie evolved, and I wanted to start with this. Now, best practice says that you need a system chart and some kind of flow process control, and that's exactly what we've got here. So up here I identified what the objects were that I was working with in my test board. I decided power on and power off would be start and end, so that's an easy one. So the whole process will start and end with providing power to the circuit, and it operates in standby mode. If you press the switch, no, so you go around in standby mode. Oh, we got to, so now we're in blink mode. We go around in blink mode until we press the switch. Yep. And then we're in dash mode. And what's missing from there is another mode switch. Yes, back to standby mode. So that's actually missing from this flowchart because why I've programmed it, and I haven't closed this loop. If it's pressed again, it'll go back to there. So I've just realised there's a mistake in this and I need to change it. Well, there you go. That's good enough for what I was doing. Okay. So this way it'll only ever get to dash mode, but I want you to be able to go back to standby mode and go back through the loop again. So that's required at the bottom there. And here's the code. If mode switch, set the mode, run a case statement, set the states based on what mode you're in, outputs, delay, and loop. Nice simple bit of code. Up here we've got our states. So in standby mode, these are the object states. Alright. So there's on, off, or blinking. They're the 3 states. This is blink mode. So you can see these are both off. Blink's blinking and mode's blinking. And the blink rate is the same for both of those. And in dash mode, they're both on, no blinking lights. So the mode switch is on. So the blink is the only one that's off. And here in the standby mode, these are both off. In fact, all 3 of those are off, and the only thing that's blinking is, and it blinks at 1 second intervals. Right, so that's it. Right, we're 3 minutes in. I've got to quickly get through the evolution. So that's that. From there, I went and did a wiring diagram. So there's my test circuit. These circuits are self-explanatory. This is version 3.1. I think I've spoken about these, but I've developed the unit test, which means I want to test the program and I need a 5-volt system. So out of this, I've got a subsystem for proving the unit test to prove that program. And there's a circuit that I've checked with the engineer is fine, and that will test. So the engineering's all done. Everything's done. What have I got left to show you? Oh, the code. Here's the code. So here's my test board. I modified the blink program, set up and declare the objects, the states, inputs and outputs. Read the switch. If it's true, if it's been pressed, make sure it got pressed for you get bounce, ignore bounce. If we got bounce, we've got a false positive, piss off. Alright, otherwise set the state. Set what mode, set the mode. Case 2, blink mode. Case 3, taillight mode. Setting those states as it was in our design, and the default will be standby mode. Write them out, loop. And there it is, all done.
Okay, so thanks for tuning in and watching me get to this point with the dash. The next stages of the dash are to do some investigation as to the Australian standards. Now, I bought these connectors on eBay. The manufacturer claims they meet international standard, and I've got to check whether or not the international standard equals the Australian standard. And I'm taking the manufacturer at his word that, that this does meet international standard. I guess I can do some testing of some of these connectors. I want to make sure that I'm being as professional as I can be. So the next stage for Project Zoomie is to sit down and develop all of the unit tests to make sure that I've done enough testing and enough research from an engineering standard that if someone says to me, what did you do? And I can show them a list of things that were done to say this was what we did to meet standard, best practice, standard, documentation. It's all here. And I'm documenting the project as I go. It's staying with me. That will all get translated to digital format and stored away on the cloud so that if someone ever says to me, where's Project Zoomie, I can show you a YouTube video. You can see on these YouTube videos I'm keeping a record of what I've done. And, this is as good as it gets in terms of a small team, in this case a one-man team. How can a team be one person? Well, the answer is you fulfill all the roles, you do them yourself. And maybe I'll bring in some students and we'll do some teamwork with some of the students from the university that are trying to do their IAP, and I can get this ratified through a professional engineer somewhere who might donate his time to us, that we can get some accreditation. So my whole aim of doing this too is to get some points towards my professional accreditation, as well as inform you guys. So I've got a record of everything. I've got a beautiful cup of tea going here. Great news. Look at this. So in terms of Project Zoomie dashboard, rewire and clock repair. Clock repair is done. It just needs to be wired into the circuit. So I'm investigating a 7803 voltage regulator to wire it in circuit in line with the circuit design. I've got a circuit design which I'm going to check with a registered professional electrical engineer who's happy to donate a bit of time to me. So if I can get him to sign that off, if I've got to pay him a bit of money for that sign off, then I'll pay him, but hopefully he'll donate his time. And then I'll have a professional point at where I can move forward from. And I've done everything as per Australian standard and per best practice. And we're moving forwards. What I could have done was order the bits on eBay, throw them on the bike and go away at my leisure. But what I'm thinking about doing is, instead of having constant current to the dashboard LEDs, I'm thinking about using a 555 timer to blink them on and off in the same way that your neon lights are blinking on and off. They can blink on and off faster than you can pick up that they're blinking, right? So I've only got to get them up to around 50 hertz blinking on and off. 50 hertz is good enough, you know, 60, 70 hertz. Your TVs blink at about 80 hertz. Anywhere around there, if I'm just blinking them on and off, you know, and then I can modify the duty cycle with the potentiometer around the 555 timer. So if I can change that duty cycle to make them brighter or dimmer, and that way everything's getting the same current, and it's not as big a current draw on the bike. So that's my thinking. And with the 7.8, using a 7803 voltage regulator to run the clock can all go in the same box, and then I can think about a fuse panel that sits in the project box, and that if you take the lid off it, you can see the circuit board will be there. It'll all be inside the box, and if you've got to put in a new 555 timer, you can put in a new one, or if you've got to put in a new 7803, you can put one of those in. So the way I'm thinking is that this thing should go for years and years and years and years, but if you've got to rip one out and put a new one in, it's easy to get to. And if you've got to change a fuse, it's easy to get to, that you can change the fuse, and it'll be secured via a couple of screws or over a panel, and you take the screws out of the panel. So the next thing is to sort of develop this circuit correctly. I've already gone away from redesigning blinkers. Someone's already done that, and I'm just buying the redesigned components, putting them straight into the bike, making sure that I test to make sure that the bike's not going to blow them or blow up using that product. So I'll be doing that, a test with the bike, isolating that circuit and doing it as a test. So I've already got all that under control. I think if I do a 555 timer around the dash light, there's no reason for them to be constant current. There's no reason for it. They can blink on and off and save on the component too. If they're blinking on and off, they actually are better for the LEDs apparently. So I'm thinking it through. I'm just trying to get my head around whether I just use a 555 timer or whether I use my Arduino. I can use an A-Tiny for this job. I've got some A-Tinys, some Arduino based stuff I can use around those. I can blink the light off and on with an A-Tiny. Or I can use an Atmega 328 or whatever they are. That I've got hundreds of these PICs and microprocessor PLCs floating around here, and I could just use one of them, program it up to blink the dash lights, and then use the potentiometer to vary the duty cycle. Alright, I'm thinking it through too much, I think. I can use the potentiometer to vary the current, right? I can do that. I can split the current and take the power out of the bulbs and make them brighter or dimmer. But if they're blinking on and off, you could do that very easily. I think that I'm in a good place with this, you know. I've got lots of options. I've got lots of ways I can go with the circuit. I've got to develop the unit test for where I'm up to. I'm going to do that, and then I'm going to make a decision about whether I want to blink my dash lights on and off. I don't think I'd do it at this stage. I think I'll just keep it simple. But if I see an advantage to doing that, well, then I might go down that road and add more componentry to that circuit. But I'm going to add a circuit box anyway. I've got to get a project box that fits the whole circuit in it, and I can start thinking about all that. So I want to thank you for getting to this far with me. This is the end of part 1 of Project Zoomie Dash, and we'll come back with part 2, which will be running through all of the unit tests and making sure that our thinking is correct and that we've tested the circuits and we've done the component tests, and that everything fits within Australian standards, and we've done sign off. We've signed off our specifications, our wiring diagrams, all that stuff. All the research is there. It's all documented, and we're ready to rock and roll on to the next bit. So we've got to make sure all our ducks are in a row and that we're all set to go on to the next bit, and all our housekeeping's done. Anyone coming along behind me can see it's all there, it's all documented, and everything's all signed off, and where I've been and what my thought processes were and where the project's up to. So we've got our project control documents here. Here they are, right, with the most current document. There it is. And I'm going to sign this off, and I'll see you in part 2. Thank you for tuning in. I want you to make good decisions and do good things. Make good decisions, do good things, keep on swinging, and we'll see you at the next one.